In the previous video, we saw how to solve the problem of implementing the switch using an n-mos transistor. The two problems were basically the poor one problem and the slow charging of the capacitor. As V output increases, the capacitor will charge slowly, which will take long time until the voltage of the capacitor reaches to the poor one. And we saw three methods to solve these problems. The first method was circuit based with a CMOS inverter and then a feedback, and we said that this circuit it suffers from feedback problems without going into the details because the details are a little bit involved. The second method, maybe we didn't talk about the disadvantage of the second method, which is technology based, using natural devices with zero threshold. This is a very good solution. However, there is a problem, a technical problem. Maybe it's hard to explain here. It's called sub-threshold conduction. Sub-threshold conduction, which leads that these devices are going to conduct during the static operation, causing static power dissipation. So there will be high static power dissipation here. High static power dissipation. This is the disadvantage of the second method, which is using the natural devices, the devices with zero threshold. So there will be high static power dissipation in this method. Without going again into the details, because the details are a little bit complicated, but you should know that the disadvantage of this method is high static power dissipation. And the third method was to replace the n-mos transistor with a transmission gate, with an n-mos and p-mos. So this transmission gate, as we explained before, it represents only one switch. So one switch is represented by two transistors, okay, n-mos and p-mos. And we saw that using this transmission gate, it will solve the poor one problem. So the capacitor is going to charge to VDD. And when the capacitor discharges, on the other hand, we checked if there will be any problem in the discharging. We found that there is no problem in the discharging. The capacitor is going to discharge to zero if it is supposed to be low. So the low will be zero and the high will be VDD. So we overcame the poor one problem. At the same time, we overcame the problem of slow charging the capacitor. Why? Because always there will be one of the transistors on with VGS or VSG. Doesn't depend on the voltage of the capacitor. So for example here, while the capacitor is charging, the PMOS will be always on with VSG equals VDD always, regardless of the voltage of the capacitor. So the speed of charging will always be high. So this p-mos transistor will be always working fully with VSG equals VDD. So the current will be always high. The current that charges the capacitor will be always high, and hence the capacitor will be always charging with high speed. The speed will not decrease as the output increase. Maybe it will decrease a little bit because the n-mos is going to turn off, but again, it will be charging with full speed of the p-mos transistor. If you compare this to implementing the switch with one transistor only, you will find that the speed here is much higher than implementing the switch using n-mos transistor only. Same here, when the capacitor is discharging, in the beginning it will discharge through two transistors, which is a very high speed for discharging. Even if the p-mos turns off, the n-mos will be working fully with VGS equals VDD. VGS of the n-mos will not be affected by V output, by the voltage of the capacitor. So even if the voltage of the capacitor is decreasing, the n-mos will stay working fully with high current, and the capacitor is going to discharge with high speed. And if you compare this to the implementing the switch using n-mos alone, you will find that this will give you higher speed than implementing the switch using n-mos transistor alone. So this is basically a summary of what we said in the previous video, the disadvantages of every method: feedback problem, high static power dissipation problem, and hence the transmission gate is considered to be the best solution, and this is what we are going to use in order to implement our gates. Let's now look at a couple of examples. to implement logic gates using that transmission gate. So from now on, we are going to implement our gates using that transmission gate. And my advice to you is when you implement any gate using the transmission gate to implement the switches, first do your implementation using switches, just switches without any transistors, and then at the end you replace the switches with transistors. For example, let's take the first example. If we want to implement a logic function y equals C A or C bar B. So here, what I suggest is you start by just draw the configuration using switches without any transistors, and then after you do that, you replace every switch with a transmission gate that consists of n-mos and p-mos transistors. So for example, you can implement this logic gate using two parallel branches. Since we have an OR, then it will be two parallel branches, and each branch will have one switch because we have ending between two variables. So you can, for example, put C as an input here and control the switch using A. So this will give you CA, C and A. And then the other branch, you can, for example, use B as an input and then control the switch using C bar. And then this will be the output. The output will be C and A or B and C bar. This is one way to implement it. Another way to implement it is to use A and B as inputs. So you can use A as an input and C to control the switch, and use B as an input and use C bar to control the switch. Again, this will give you A and C or B and C bar. I'm going to ask you here, what do you think? Which one of these two implementations is better? Which one of them is better? I claim that this one is better. Why is that? Because here, when you implement any switch using a transmission gate, you will need to provide C and C bar. So if you want to implement this switch and to be controlled by C, you will need to provide C and C bar. So already you will need to invert the C. And then when you convert the switch again, you will need to invert C, so that you have C bar and C. So you will need, for this switch, you need C and C bar. Why? Because when you use the transmission gate to implement this switch or this switch, you have n-mos and you have b-mos, right? And if you want to control the switch using C bar, then you put C bar to the n-mos and you put its invert, which is C, to the p-mos. So if you want to control this switch, you will need C and C bar, and if you want to control this switch, you need C and C bar, so you will need to invert only C. But A and B, you don't need to invert them. But here in this implementation, I claim that this implementation, this is not efficient. Why? Because in order to control this switch, you need C and C bar. You need C bar to go to the n-mos and C to go to the p-mos. And in order to control this switch, you will need A and A bar. Why? Because A will go to the n-mos and A bar will go to the p-mos. This switch will be implemented using an n-mos and p-mos. So you will need to invert A and you will need to invert C. So you will need one more inverter here. You will need one more inverter, which means you will need two more transistors to invert A. For example, let's complete the implementation. Here, for example, if you want to implement this circuit using transistors, then you have C. Then you are going to use, in order to implement this switch, you are going to use a transmission gate like this, which consists of n-mos and b-mos. And this switch is controlled by A, so A must go to the n-mos and A bar must go to the p-mos. And then the second branch, B, there is a switch, so we are going to use a transmission gate, n-mos and b-mos. Hopefully you can see it. And we need this switch to be controlled by C bar, so C bar goes to the n-mos and C goes to the p-mos, and then we connect these two here. But in order to get the A bar, you need to invert A. You need to invert A, right? So you need an inverter here. And in order to get the C bar, you need to invert C. So you need an inverter for C here, right? So here, how many transistors did we use? We used 1, 2, 3, 4, in addition to 2 inverters. 4 plus 2 inverters. Each inverter uses 2 transistors, so you need 8 transistors. While if we implement our gate using this structure, we will have A as an input and then a switch here, which consists of n-mos and p-mos transmission gate. And this switch is controlled by C and C bar. And then the other branch, B, and then a switch, again transmission gate, n-mos and p-mos. And this switch is controlled by C bar, so the same C bar here can be used to control the p-mos of this transmission gate and the n-mos of this transmission gate. And here there will be C. And then this is the out. How many transistors did we use here? We used 4 transistors plus only 1 inverter. We needed to invert C only, right? So one inverter means 2 transistors, so this will give you 6 transistors total. So here, when we compare these 2 implementations, since we already have C and C bar in the equation, then we can use C and C bar to control the switches, because already for each switch we will need to invert C, so why we don't use it to control the other switch? But if you use another variable to control the other switch, then you need to invert also the other variable and add one more inverter. So this is one example here to implement this logic function, and this is the efficient way to implement it. And as I advised you, try to start always by putting the configuration using switches, and then you replace every switch with a transmission gate. Let's take another example. Another example says we need to implement the XOR function. And the XOR function says the output equals A B bar or A bar B. So here, in order to implement this function, again we have 2 branches, and every branch will have a switch. So you can implement in multiple ways. You can use A here and B here, and then this switch is controlled by B bar and this switch is controlled by A bar. Or you can use A and A bar as the inputs. For example, you can use A as an input and switch is controlled by B bar, and then you can use here A bar as an input and the switch is controlled by B. If you think about which one is optimal here, both of them will be the same. Why? Because in both of them you will need to invert A and B. You will need to invert A whether you use it as an input and as a control, and you will need to invert B whether you use B and B bar as controls or use one of them as a control and the other one as an input. In all cases, you will need to invert A and you will need to invert B. So it doesn't matter. So we will go with one of them. So let's go with this implementation. So here, if we go with this implementation, we have a branch with an input A, then this switch, we replace it with a transmission gate, n-mos and p-mos. Don't forget, every switch will be replaced with n-mos and p-mos. And then this switch is controlled by B bar, so we'll need B bar here and B here. Then the other branch is A bar, and then we have a switch, we replace it with n-mos and p-mos. And then the output. This switch is controlled by B, so the n-mos will take B and the b-mos will take B bar. So now, this B can be used to control these two transistors, and B bar can be used to control these two transistors, and B bar can be obtained by an inverter of B. So this is B, it will be inverted, it will give you B bar. B will be used to control these two transistors, B bar will be used to control the other two transistors. How many transistors did we use here in this implementation? 1, 2, 3, 4. We have 4 because we have two switches. Each switch has two transistors. Transmission gate, right? So two switches. And how many inverters? We used one inverter for B, but also we need here one inverter for A, right? We need one inverter for A. So here, two switches and two inverters. Two switches, each switch has two transistors, and two inverters, each inverter has two transistors, so total we'll have 8 transistors. So total we have 8 transistors. However, this is how we implement it. Of course, you take this A and you take it here to invert it. However, when you plot it in the exam or in a quiz, you don't have to make all the connections like this. You can just plot it in an easy way. You don't have even to plot the inverters in details, like you don't have to plot the transistors inside the inverters. All what you need to do is you need to just plot it in a simple way, but you take care when you count the transistors. So for example, this circuit, if you are plotting it in your homework or exam or quiz, what you need to do is you will plot the transmission gates, n-mos, b-mos. You say this is A, this is B bar, this is B, and then you plot the other one. With A bar here and B bar here, and that's it. You don't have to show the inverters. You don't have to plot the transistors of the inverters. You don't have to make even the connections, the long connections. You don't have to make, but you have to count the inverters. Take the inverters into account. When you count the number of transistors, you say that we have 4 transistors plus 1 inverter for A, 1 inverter for B. So 2 transistors to invert A plus 2 transistors to invert B, so total 8 transistors. You don't have to make these long connections between B bar here and B bar here or complicate the circuit. It's just easy figure, but you have to take care when you count the number of transistors to take care that you need to invert B once, only once. You don't need to invert it twice because it's the same B bar. You need to invert it once and you need to invert A once. So total will give you 8 transistors. That's it for this example and for our course. I wish you all the luck in all future courses, and I hope that you benefited from these video lectures, and best of luck. See you in other courses in the future, inshallah. Assalamu alaikum.